Hello everyone. In this video, I will explain a concept called as a quadrature carrier multiplexing. As you know, multiplexing means transmission of multiple signals through a common channel. Now in this quadrature carrier multiplexing, what exactly we are doing is, we are transmitting two independent message signals, okay, by modulating using the same carrier, but the carrier applied are in phase quadrature. That's why it is called quadrature carrier multiplexing. Now, see, yeah. Now, in the Costas receiver, whatever I explained in my previous video, if you have seen, quadrature null effect can be overcome by using that coherent or Costas receiver. The same concept can be extended even here also for a quadrature carrier multiplexing. Now this quadrature carrier multiplexing is also called as quadrature amplitude modulation, because this process is a type of double sideband suppressed carrier signal only. The output what we get here is a two independent DSB-SC signal, okay, by modulating using a quadrature carrier. And the advantage of this quadrature carrier multiplexing is, as I told, multiplexing means transmission of multiple signals through a common channel. Now, in this case, we are transmitting two message signals by DSB-SC signal by wave, okay, and both signals actually occupies the same channel bandwidth. This is the advantage of quadrature carrier multiplexing. And in the receiver side, it is possible to separate the two independent message signals. So basically, you can call this as, or this method, quadrature carrier multiplexing or quadrature amplitude modulation, as a bandwidth conservation system, because we save the bandwidth, because both are transmitted using the same bandwidth and separation is possible. That is the beauty of this particular method. Now, going to the transmitter and receiver block diagram of this, because as I told earlier, whatever that Costas receiver, where we use this quadrature carriers and all in the Costas receiver, same concept is actually used in this method also. Now this is the transmitter of a QAM or a quadrature carrier multiplexing. This is the receiver block diagram of a quadrature amplitude modulation. Now, so as I told here, we are actually having a two independent message signals. The first one is M1 of t, let us say, okay. The first one is M1 of t, and the second one is, this is M1 of t, the second message signal is M2 of t, and we are transmitting the both message signals by modulating using the same carrier. But as I told earlier, we use a quadrature carriers. The frequency of the signals are same, but both are 90° out of phase, or you can say quadrature in phase. The one is cos, the other one is sine 2 pi fct. So I am using a 90° phase shifter here to change the phase of this carrier by 90° and apply to the Q channel. I call this as a Q channel again, this as the I channel. Okay. So since I'm using a multiplier over here, a product modulator, and I'm multiplying a M1 of t with the carrier. As you know, when you multiply the two signals, the output of that signal is always a double sideband suppressed carrier signal. So we get a double sideband suppressed carrier signal over here, and in the Q channel also I'll get a double sideband suppressed carrier signal. Now both are added together, and we get a multiplexed signal called as S of t. Now this S of t is given as input in the receiver side over here, and using the same carrier cos 2 pi fct, okay, whatever I have used in the transmitter side, the same carrier, the recovery of the message signal is done, both M1 of t as well as M2 of t. The concept is again same. I'm using a 90° phase shifter, I get a quadrature carrier over here. The same S of t is given as input for both the product modulator I channel as well as Q channel, right? And I'm using a low pass filter which allows only the low frequency component, and in the output of that we get a M1 of t and M2 of t with certain amplitudes. Okay. Now let us see what are the equations actually we get in the output of a QAM transmitter and the QAM receiver. As you know, in the previous case, we are actually having this sum of the two outputs of the product modulators. The output of this is given by M1 of t multiplied by this cos signal, right? And the output of the second product modulator is M2 of t multiplied by AC sine 2 pi fct. So accordingly, when I add both the signals, I will get this particular equation. So this is from the top product modulator. This is from the bottom product modulator. That is AC M1 of t cos 2 pi fct plus AC M2 of t sin 2 pi fct is your multiplexed signal S of t. Okay, which occupies the same bandwidth of, let us say, 2W, where W is the highest frequency of the two message signals, M1 of t and M2 of t. Okay, so we call this AC M1 of t as the in-phase component, AC M2 of t as the quadrature part, because it's the quadrature carrier, this is the in-phase carrier, what I have here. Now these signals are given to the receiver again. Okay, so this is your again receiver block diagram, where the S of t is given. It's a coherent demodulation technique what I am actually using over here with the two different carriers, quadrature carriers. Now the output of this is given by half of AC dash M1 of t. The output of the bottom channel coherent detector is half of AC dash M2 of t, where AC dash is the amplitude of this carrier, which can be different amplitude, but the frequency and the phase of both the carriers, whatever I'm using here in the receiver and the transmitter, should be same or synchronized or incoherent all the time. Okay, if they are not coherent, again we face actually problem with the demodulation. We may get a quadrature null effect, and that quadrature null effect can be overcome by using a phase discriminator and VCO, as I have explained in my previous video in the topic Costa's receiver. Now, as I told, they have to be synchronized, and relations between the oscillators and should be same, and all those things I have explained. And what we can use is a Costa's receiver technique we can use over here also. Now I will explain how a message signal M1 of t is recovered in the top channel, that is I channel, by using simple derivation. Now, as you know, the S of t given to the first product modulator is the signal, which is the input, a multiplexed signal. The local oscillator will produce a signal which is given by AC dash cos 2 pi fct. Now the output of the top product modulator is nothing but it is the multiplication of that S of t with the carrier, that is C of t, let us say. Okay, so when I substitute this S of t and C of t into this particular equation, what I will get is this equation, where this first part is S of t and the second part is the carrier, that is AC dash cos 2 pi fct. So when I multiply these sum terms with this particular carrier, I will get this particular equation. Okay, so where this AC dash cos 2 pi fct is multiplied with both the terms. Fine. Now here we have a cos 2 pi fct and cos 2 pi fct. I rearrange the terms and I have a 2 times the cos term. So we get cos square theta. That is AC dash cos square 2 pi fct into M1 of t. And the second part, it is again rearranged AC M2 of t sin 2 pi fct multiplied by AC dash cos 2 pi fct. Now here I apply a cos square theta rule, and here I apply a sin A cos B rule. So what I will get is this equation. So cos square theta is equal to 1 plus cos 2 theta. So here when I apply, I get a cos 4 pi fct. Okay. Now in this second part, again when I apply a sin A and cos B rule, I'll get something like this. So sin of 2 pi fct minus sin A minus B plus sin A plus B. So this will give you 0, and I'll get only this particular term multiplied by this term. So when I pass this component, the entire component, through a low pass filter, this is the high frequency component, this is a 0, this is a high frequency component. So my low pass filter will eliminate these components, and it allows only AC dash by 2 M1 of t multiplied by 1 is that term itself. That is, the low pass filter allows only AC dash by 2 M1 of t. Fine. Now in the same fashion, when I apply the same S of t to the bottom channel, that is quadrature channel, and multiply with AC dash sin 2 pi fct, what I will get is the message signal. You can verify this by using the simple trigonometric mathematical rules. I will get this signal. So what I can say over here is, in the both channels, okay, I channel and Q channel, this M1 of t and M2 of t with this particular amplitude is actually recovered. Okay, so the quadrature amplitude modulation is actually used for multiplexing the two independent message signals, and without any mixing, the two signals M1 of t and M2 of t can be recovered in the receiver. Thank you for watching this video.